I would like to discuss today Brownian simulations and boundary conditions. So we would like to see how a Brownian process should be dealt with when we are at the boundary of a domain. So let me first introduce the question and the problem we are interested in here. So let me remind you what is Brownian simulations. So Brownian simulations, and so the basic idea is to go back to the Euler scheme. So if we have x of t, which is a stochastic process, for example, which is a Brownian motion, so we know that x of t satisfies the equation x dot is equal square root of 2dw dot, where w is the standard Brownian motion with variance 1, so d is called the diffusion coefficient, so it is basically the variance diffusion coefficient, which represents the variance of the process. Then how to simulate this process? Well, the Euler scheme says that xt plus delta t equals xt plus square root of 2 delta t and xi, where xi is a Brownian Gaussian variable. And so you can, for example, generate it in MATLAB using around n. Right, and this is called the classical Euler scheme. This is Euler scheme. And so how does it work in practice? Well, you start at a point x0, let's say. Then with this process you generate a point x1 and then x2 and so on, x3, x4, x5, and then the representation is that you generate the path between those points, and this is how we are generating a random walk at the scale delta t. So this is the procedure to generate a random walk at scale at the scale delta t. Okay, and up to now there was no boundary because this is how the path and the random walk is generated in the free space. And what we call Brownian motion, the Brownian motion is actually obtained in the limit of this procedure as delta t goes to 0. There is a construction which comes from the mathematician Paul Levy, which says that once you have a path at the scale delta t, you can construct a path at the scale delta t divided by 2, and this is obtained by you start with x0 and then you have an intermediate point, let's call it y1, and where you can generate at this time step delta t divided by 2, and then you get an intermediate point, and you can repeat the procedure for the point x2, x1, and so on. So you get from this procedure a construction of a refined random walk at the time scale delta t divided by 2, such that the point x1, x2, xn are fixed. All right, and so the construction, this procedure is summarized in, I will give for reference the book of Schuss in 2009, published in Springer, about stochastic processes. So now the class of today concerns what happened when we are interested in the simulation of a Brownian path inside a domain. So suppose a domain is given, and again we repeat the previous procedure, and the question is what happened at the boundary. So at the boundary we have to decide what we are doing, because the boundary can be artificial, or it can represent in physical conditions, it can represent a reflecting wall or an absorbing boundary. So in general, if we have a domain in a simulation, and if we have a Brownian path from moving to point xn to point xn plus 1, is usually achieved by this jump. So in general, the particle in the simulation jump over the boundary. However, if, for example, we would like to impose some conditions such as absorbing boundary conditions, saying that when the particle go over the boundary, the process should stop. So let's do it in dimension 1. This is the dimension 1, and we have a jump process that can move. So we start at position x0, then move to position x1 according to the scheme that we previously discussed, the Euler scheme, until we arrive to position xn. And suppose at the next position at xn plus 1, we go over the boundary. So this is the boundary. So at this and this is xn plus 1. So at this moment, if we decide that the boundary is absorbing, so let's discuss now absorbing boundary condition. Absorbing boundary conditions. Then which means that the particle, the trajectory should be terminated. So the trajectory is terminated. So what does it mean that the trajectory is terminated? Which means that we end the process after xn. So we have an ensemble of points, which is x0 until we arrive to xn. And this is the path. So now we can ask, the question is, what is the associated probability distribution function for this process? So let's discuss now this probability density function for such a process. Associated to Brownian motion, we know that the probability density function satisfies the equation dp dt equals d Laplacian p. So if at the boundary a process is terminated, let me recall that P by definition, this is the probability that for a process x of t to be located at y plus dy, condition that it started at position x, then this probability is given, can be formulated with this probability density function as pt of y condition on x dvy. So if at the point x, or let's call it the point x equals a, we have an absorption, it means that the probability to make a transition from that point inside the domain is 0, because by definition the particle, the Brownian particle, has been absorbed. So by definition we have pt for y equals a, conditioned that we started at x, this is equal to 0. That is the probability to start at y and to make any transition inside is 0. So this is the absorbing boundary condition that should be given at such a point. So this is for the Brownian motion, and the condition is a little bit more complicated for actually this random walk, because for the random walk the process does not hit the boundary but jump over. So for the random walk we will discuss in a different class how we give boundary condition, because this is associated to jump processes. So now I'm going to discuss the reflecting boundary condition. So again, let's suppose we have in one dimension a process that only lives in the line 0 plus infinity. So again, we have this process which is the Brownian motion, and we impose that the process cannot leave the boundary, which means that after xn, if we run a simulation and the process move outside, then the question is, what do we do with this point xn plus 1? And for this, I would like to start with the probability distribution function of such a process p, which satisfies the equation the same as we've written before in dimension 1, which is dp dt equals d, diffusion coefficient, d dp dx squared. And so saying that the process lives inside the line 0 to infinity, which means in here, it says that the probability to find the particle at any moment of time, knowing that it started at position x, at position y, if we integrate dx over 0 to infinity, this has to be equal to 1. So if we differentiate this with respect to time, then what do we get? We get that integration from 0 to infinity of dp dt equals to 0. Now using the equation itself, we obtain that this is equivalent to d dp dx squared dx equals 0 from 0 to infinity. So now if we integrate this and we use the fact that at infinity dp dx converges to 0, dp dx converges to 0 when x goes to infinity, then we are left with the condition that dp dx has to be equal to 0 at the boundary which is here located at 0. So this gives us the condition on the probability density function. And now we would like to construct the associated process. So for this, we are now going to construct the solution of the diffusion equation construct the solution P with the boundary condition which is given by this boundary condition. dp dx at x equals 0 equals 0. So how do we construct such a solution? Well, the solution can be constructed by using the reflection principle, which means that the probability to switch from y to x during time t in dimension 1, this is given by the exponential of x minus y squared divided by 4 dt. And then we have the normalization constant, which is square root of 4 pi dt, plus the same quantity, except that now instead of having minus y, we have the point plus y. So plus y divided by 4 dt. So by definition, if we differentiate this, so again, let me explain what we're doing. We have a point, let's say the particles start at the point y at time 0, and this is the probability to jump to a point x during time t. Right, so the possibility to make such a jump is to go directly, or if there is a reflection, would be first to touch the boundary and then being reflected. And this is what this equation says. And so if we differentiate this with respect to x and we calculate at x equal 0, so if we differentiate the first term, we'll get basically the exponential term will remain, but we'll have the minus x minus y plus the with a x plus y with a minus sign multiplied by minus 1. So which leave us with only minus 2x, since the y cancels, and multiply, of course, by the exponentials. I didn't put here, we have to multiply everything by the associated exponentials, and here again. But when we put x equals 0, then we are left here with 0. Because the exponentials are the same. The term in the exponential are the same in here, that I didn't write. Okay, so this shows that actually we have the probability density function, which could also be true if we replace x by minus x, right? So it's clear that in this expression, if we replace x by minus x, we obtain the same things. And this suggests that we can now use this as the probability distribution function for the process, which is the absolute value. That is for the process absolute value of x, which give us precisely the law that we need for reflection. That is, we have now the Euler scheme for the stochastic process, which is x of t plus delta t. So what is this equal to? If nothing happened, that is, if we are still in the right part of the line, then we just use the classical Euler laws, which is xt plus delta t equals xt plus square root of 2d delta t, and then we have psi. So this happens only when this quantity is positive. So when everything here is positive. However, if it is negative, then what we should use instead is just make a reflection, which is to use then minus this quantity. That is, we have to rewrite everything xt, but instead use the same quantity with a minus sign. So this is 2 delta t, and then we have psi. Right? So this is how we are going to reflect a Brownian motion at a point where there is no flux. Let me now just mention that this is to check this. The probability distribution function that I wrote was actually for the Brownian motion, but we can write the probability density function for the jump process, which is probability of making a jump to the point y at time t plus delta t. This probability can be written using this Chapman-Kolmogorov representation, which is the probability that the particle started at position x and time t, multiplied by the transition probability. Since we have a Gaussian, this is just given by minus x minus y square divided by 4d delta t divided by square root of 4d delta t. So this is for the first part, plus what we have found, which is the reflection term, x plus y square divided by 4d delta t, and this is everything divided by 4d delta t, and I have forgotten here the pi that I'm going to add. And now we have to integrate over all dx and over the line from 0 to infinity. And again, the same calculation as I have done before. If we differentiate this probability with respect to y and calculate it at y equals 0, this gives us this reflection boundary condition. So I would like now to continue with a generalization. How do we generalize this? So the same can be calculated for a general stochastic process when we have a drift x dot equals a of x plus square root of 2d of x w dot. Then the same analysis can be done to obtain what is the zero flux boundary condition. So zero flux boundary condition, if we have a line, which means that there is no flux, so the system or the stochastic process is confined only in this positive part, 0 to infinity. And again, using the same calculation that I have done previously, I invite here you to write, so let me write the Fokker-Planck equation associated to this is dp dt equals, so let's suppose d is constant, so this is d dp dx squared minus a of x ddx df of x p. So the zero flux boundary condition, now instead of having just d dp dx equals 0, so I invite this to the reader as an exercise. This is dp dx minus a at the point 0 multiplied by p at 0 equals 0. So this is at x equals 0. So this is a zero flux boundary condition, and similarly the process can be reflected. So if x, the point, is here at xn and has to jump for the next one at xn plus 1, then xn plus 1 is just reflected inside so that this condition is maintained. So now let's move on. There is another interesting condition which is called the Robin boundary condition. Robin boundary condition, and this condition says, this is also the partial flux, which said that instead of having dp dt, which is pure reflecting, equals 0, you can assume that there is a leak, and so dp dx is, for example, the flux is proportional, it is loss proportional to k times this probability. Sometimes you can find in the literature when it has to do to a channel, modeling of how ions are absorbed to a channel. There is also a term which can be another constant k2 plus a probability p. And sometimes we can also have here a certain power. So this is empirical, this construction of boundary condition associated to channels. So let's summarize this as a condition saying that dp dt, dp dn at the boundary x equals 0 is equal to minus kappa p. So what does it mean, partial reflecting boundary conditions? It means that you have a line, then a process moves, this is a stochastic process, and then what happens? With a certain probability, the process can be terminated if it jumps. So it is terminated with a certain probability. So either the process is terminated, this is one possibility, or it is reflected. And so it can be terminated with a certain probability p that we are going to, so let's call it capital P to make sure that, so it can be, it can be terminated, it can be reflected with a probability p, capital P delta, square root delta t, or it can be reflected with 1 minus this probability, 1 minus p square root delta t. And the question is how to link this capital P here with this kappa. And so let me just summarize this with the following rules. X of t plus delta t equals, so it is reflected, so we take if the point has been crossed. So let's write it. I'm not going to write the entire equation, but we have already written it several times. This is minus x of t plus square root of 2d delta t multiplied by xi. So if this is negative, which means we have crossed, then we put a minus, this, so it becomes positive. And this we will do it with a probability, 1 minus capital P square root delta t. Or there's another possibility, is that the trajectory is going to be terminated. And what is the probability of this? This is precisely the opposite. So it's P multiplied by square root delta t. And I will not show this in here, but there's a relationship between kappa and capital P, and this is given by the following equation. Kappa equals capital P divided by square root of pi, and this is in dimension 1. In higher dimension, so this is in dimension 1, and in higher dimension, it's a little bit more complicated. It's still P divided by square root of pi, but then we have to multiply to the normal derivative. It is a normal transposition of the normal multiplied by the matrix, the diffusion matrix D multiplied by n. This is a D is a tensor here, and so here this is a number. And when we have an anisotropic diffusion, this counts. Finally, I would like to mention that it is always possible to reflect also objects such as rods. If you have a rod, it has to be reflected at a boundary here. But then the condition for reflection is more complicated, because we have to reflect, actually, this is a problem in 3 dimensions, because there are three variables to describe the rod. There is the position x and y and the angle theta. And I'm not going to discuss that here, and probably in the next lecture I'll discuss how to reflect a rod in dimension 2, which should be reflected really in a 3-dimensional domain. So for those of you who are interested, I refer to this publication from 2008 in Siam Journal of Applied Mathematics, where we discussed this partial reflection diffusion, and in particular how to reflect in high dimension. And also for stochastic processes, I have referred to the book of Schuss about stochastic processes.